So, chapter 17 is the last chapter of Physics 213, and and the focus is on waves. So, depending on depending on the relative directions of the wave oscillation and the wave propagation direction, we can actually cast the waves into two different categories. One is called one is called the let's see the pointer. Where is it? One is called the longitudinal waves. So if you have the wave that say the wave oscillation is in this direction, to the left and to the right. So this is the way um, this is the way this is the way oscillation direction. And then you have the wave that's propagating at the same time the wave is propagating that say in the rightward direction. So this arrow indicate the wave propagation direction, and this wave oscillation direction indicate the that say molecules being forced to move to the left and to the right, and then in the meantime the wave is propagating through the through air in the rightward direction. Now, if you have the wave oscillation or the particle oscillation is in the same direction as the wave propagation direction, this kind of wave we call that longitudinal waves. As there's a let's say a sound wave is longitudinal wave. Now there's another wave propagation that there's another another type of wave when you have the wave that is oscillating up and down like this. So the particle is oscillating up and down like this, but the wave direction is in the rightward direction. So in other words, if the if the particle's oscillation direction is perpendicular to the wave propagation direction, this kind of wave we call that transverse wave. So these transverse waves, for example, electromagnetic wave is one type of is considered as transverse waves. Mechanical waves is also a transverse waves. Okay. Now regarding waves, let's say now you have a source. So this is the source of the wave. Now if we're dealing with a sound wave, for example, so you have a source, you have a sound source at the center, and then think of it as it's going to produce a spherical wave waves. So what's going to happen is that you have a source at the center, and then it's going to produce a wavefront, and then it's propagating away from the source. So we have a wave that's propagating away from the source. So this arrow indicate the directions wave propagation, and we can connect dots. We can connect the other points where they all have the same oscillation amplitude, and then draw a circle. So every point on this circle will have the same amplitude, and so this form, this is what we call the wavefront. So the wave will produce, many wavefronts, and usually we pick the amplitude. We pick the points where the wave amplitude reach the maximum. So you have the wavefront. This is the one wavefront. This is another wavefront, and of course the amplitude of the wave at this point and at that point, they are different. And so sound actually can travel in air and can also travel in liquids and also can travel in solids. So that is why when you let's say you swing on the water, you can still, if you produce a sound, people on the water can still hear you, because the water molecule then act as a medium for the sound wave to propagate it through. Okay, so the sound wave basically is produced by let's say in air. So when you have a source in air that produces sound wave, the air molecule is being modulated. So there are places where the air molecules you have higher density. There are places where the air molecule has a lower density, and thus you can produce that. That's how the sound is transmitted through air. Likewise, on the water, you have water molecules, being forced to, move by the pressure variations of the source. Okay, and also in solid as well. So the speed of sound, if we're dealing with ideal gas, Then the speed of sound can be calculated using this equation. So you have you have this equation, okay? And this equation, this v, of course, is the speed of sound, and that's equal to the square root of gamma, which is the specific of sound, gamma is the ratio of specific heat. Okay, and you have your R, which is the gas constant, and temperature, that's your T, that is the temperature in Kelvin, and you have the M. M here again is the molar mass. So if you have the let's say in air, then the molar mass is roughly probably close to 28 grams per mole, because the majority, the dominating species uh, near the surface is the N2 molecule. Okay, so this is the equation that if you don't know the speed of sound, if it's not given, and the temperature and the air molecule is given, the molar mass is given, then you can you can use that equation. There's also another equation that is the speed of sound is equal to let's see, let me just write here. There's another equation that also deals with the speed of sound, which is an empirical velocity, and that is v equals 343 meter per second. That's the speed of sound at room temperature, and then plus 0.6 times the temperature. Now in this case, the temperature is expressed in Celsius. So this equation so this equation and that equation, they all deal with the the speed of sound. But then this equation is when you are given the temperature and also the molar mass, you can calculate what is the speed of sound. And this equation is when when the temperature, when you are you are given the temperature expressed in Celsius, then you can calculate the speed of sound. Okay, and when we are dealing with waves, there are several wave parameters which you're already familiar with. But let me just give you a refresher. So when you're dealing with wave, of course, the following are the parameters that you deal with. Let's say frequency, angular frequency, wavelength, and also wave number. So you need to know how these parameters are related to each other. So for the for for frequency, what we know is that for any waves, regardless whether it's a sound wave, it's a transverse wave, it's a longitudinal wave, as long as you're dealing with a wave, this is the equation that governs the wave, and that is the frequency times the wavelength. That gives you the speed of the wave. Okay, so this is the equation that that is always valid. Okay, as long as you're dealing with a wave. So frequency times wavelength is equal to the speed of the wave. Now, what is the wave number? Wave number is the 2 pi over the wavelength. That you should know because we deal with this in 2000. I'm sorry, in physics 311. Omega, which is the angular frequency. So angular frequency and the periods are related by this. Okay, omega is equal to 2 pi over f. And also, if you recall, omega is also equal to 2 pi times the frequency. Okay? So these are just something that most of you should already know. So these are the how the wave characteristics are related to each other. Now, when we're dealing with the traveling sound waves, when you have something, the waves that's traveling, in other words, it does not stay there, at a fixed time and place. It's actually, it's traveling from one place to another. We can actually use the sinusoidal function to describe how the wave propagate through space and time. So this equation this equation, this is the displacement. The first equation is the displacement, and it's a function of position and time. So s of x of t is equal to a constant, which is the amplitude, the displacement amplitude, and then times cosine of, and then within the argument, that is the wave number times the position where the wave is located, and then minus omega t. Now omega, of course, is the angular frequency. T here is time. So your x and t are variables. So it depends on where the wave propagate. Okay. So excuse me. So this equation, this is displacement, that displacement, which is displacement amplitude times cosine of kx minus omega t. Now, when we're dealing with sound waves, because the sound is produced by the pressure variation, so we also have another equation that describes how the pressure of air molecules, in response to the source. So you have a pressure variation that is delta P, that's a function of position and time as well, and that's equal to the pressure variation amplitude, which is the constant, and then times sine of kx minus omega t. So we can see that the displacement and the pressure variation, they have the same argument within the sinusoidal function. You have kx minus omega t. However, in the displacement, you have the cosine, and for pressure, you have the sine, which means that they differ by 90 degrees. Okay, so there's a phase difference between the displacement and the pressure variation. What it means is that when displacement is smallest, then pressure will be the largest. When the pressure variation becomes the largest, when the pressure variation becomes the smallest, then there's the largest displacement. Okay, so that's that. Now, in addition to, so these two equations describe how to describe these two equations describe traveling sound waves. Now, imagine that if you have more than one source that produce a sound. I say you have source S1, you have source S2, and they both produce they both they both produce they both produce sound wave. Okay, so you have this one that produce a sound wave. This one also produce a sound wave, and that's that you have an observer at this point P. And so when we say observer, which means that the wave is going to propagate through space and reach the observer. So that's say the wave that is produced by source S1 has propagated distance L1, and the wave produced by source 2 has propagated a distance L2. So both sound waves are going to reach the observer. So when you have more than one wave that reach the observer, what's going to happen is that those sound waves are going to interfere with each other. So the sound that is heard by the observer will depend on how these two sound waves interfere with each other. Okay, so this kind of phenomena we call that wave interference. Okay, let's say if you have just source S1, you produce a sound wave, the observer is going to hear the sound wave. But then when you are adding another source S2, this S2 is going to produce a sound wave. So would the observer hear any sound, or what kind of sound the observer will hear really depends on how how these two sound waves interfere with each other. And to to find how they interfere with each other, well, there we found that when the distance, the path length difference, okay, when the distance difference, uh, satisfies certain conditions, then the interference that the observer here will be different. Okay, so this is a definition. This is a definition of path length difference, and that will be the distance traveled by the sound, difference of the distance traveled by these two sound waves. So delta L is the absolute value of L2 minus L1. So whatever extra distance that one of the source has traveled, that is what we call the path length difference. And what we found here is that if the path length difference with respect to one wavelength, they bear this relationship. So what a phase difference of 2 pi is equal to one wavelength difference. So in other words, if the path length difference is equal to one wavelength difference, then the phase difference of these two sound waves is equal to 2 pi. Okay, so mathematically, this is how we describe it. This phi here, this angle here is the phase difference, and basically is can be expressed in radians or in degrees. Okay, if you express in this case, this is in radians. If that will be in degrees, then this is if this is in degrees, then the in the denominator, the 2 pi will be replaced by 360 degrees. So the phase difference divided by the 2 pi is equal to the path length difference divided by one wavelength. So in other words, if delta L is equal to one wavelength or integer multiple over one wavelength, then the phase difference is equal to integer integer multiple of 2 pi. Okay, so if you rearrange this equation, you'll find that the phase angle is equal to the delta L, the path length difference, divided by one wavelength and multiplied by 2 pi. Okay, so this basically we're going to revisit wave interference in more depth when we get to Physics 214. But this will just give you an idea that when you have more than one sound, when you have more than one source that produces sound wave, they are going to interfere with each other, and and how they interfere with each other really depends on the path length difference with respect to the wavelength of the sound. So let's go back to these pictures again. So you have two sound waves, each produces, you have two sound sources, each produces sound waves, and they're going to propagate to the observer. So they're going to interact with each other. And what we found is that if the phase angle or the phase difference is equal to 2 pi times integer, and that integer is equal to 0, 1, 2, or 3. So in other words, if the phase difference is equal to 2 integer multiple of 2 pi, then we call that kind of interference as fully constructed interference. So in other words, if you look at this picture, let's say you have one wave source that produce that smaller amplitude that produce this kind of sound waves, and you have another source that produce a larger amplitude of the source, but then they are in phase. When I say in phase, which means that the peaks the peak of the source one is equal to the peak of the source two, or the amplitude when peak to peak it is occurring at the same time. And when they reach the zero amplitude, they at the same time as well. So this is two wave source they are in phase. So what's going to happen is that when they interfere, you can imagine that the resultant wave that the observer is going to hear is the summation of these two waves. So when you add these two together, you're going to get a pronounced source. So in other words, a larger amplitude because the amplitude adds up. So this is the resultant sound wave. So this is what we call the constructed interference. This is called resultant. Okay, so so this is when the phase angle is the phase difference is equal to 2 pi times the integer. And if you use the equation from previous page, you'll find that the path length difference of the two sound waves over the one wavelength is equal to 0, 1, 2, 3. So these are the condition for the two waves to interfere constructively. When we say when they interfere fully constructed, it means that the amplitude of the waves adds up. So you get a very large sound because the amplitude, you add those together. Now, when you have the wave that that looks like this. You have the one source that's going in this direction, the other source that's going in that direction. So when you add them together, what's going to happen is that you get nil, you get zero amplitude, because the peak, this is positive, this is negative. When you add them together, they just cancel each other. Okay, so when they cancel each other, it just means that it is fully destructive. So it will happen that you have two, sound sources that produce the wave, but then the observer might hear nothing because they interfere destructively. They cancel each other. Okay, so this is the sound cancellation, and this is utilizing the fact that they are fully destructive. So what is the condition for them to interfere destructively? And here's the condition that the phase angle or the phase difference is equal to the odd integer multiple of pi. So you have 2m plus 1 and then times pi. Your m here is 0, 1, 2, 3. So in other words, if your phase difference is equal to 1 pi, 1 pi, 3 pi, 5 pi, then they're going to interfere destructively. And in terms of the path length difference over the wavelength, you'll find that it's equal to 1 half, 1 half, 3 halves, 5 halves, and etc. Okay, so these are conditions for the waves to either interfere destructively or constructively. Okay, and these are the extreme cases when they fully disrupt or fully construct interference. There might be situations that the two sound sources that produce the sound waves, they don't fully interfere destructively or constructively, and the interference might be intermediate. If that's intermediate, then you still can hear the sound, but it's not as strong as the fully destructive, and it's not as no sound from the fully destructive interference. So these are the wave phenomena when you have the sounds when you have many sounds, it's going to interfere with each other. Okay, and that's why when you go to a concert, when you go to a music hall, you want to find an ideal place that give you the most constructive play. You want to find an ideal place that give you the constructive interference so you can hear the maximum sound. Or if you go to a rock concert, if you think that's just too noisy, you want to find a place that would actually give you no sound because you get a fully destructive interference. Okay. All right. So when we talk about sound, one of the quantity that we're interested is the intensity, because each sound contains energy, and with energy you can imagine that, let's say you have the sound wave propagating through air and reach your eardrum, and depending on the intensity of the sound, sometimes your ear can hurt because the sound is too strong. Okay, so how do we define wave intensity? This is the equation that we define wave intensity. So we use capital I to indicate that's the wave intensity, and that's equal to the power over the cross-section area, or the area that intercepting the sound. And what is the power? Power is the rate of energy that transfers through the cross-section area. Okay, so this is the power and over the area that are intercepting the sound. So let's imagine that you have a source here at the center, and it's producing the sound wave at the producing sound wave at the power that's called that P, and then there's some distance away from the sound. Let's say what is intensity that is our distance away from the sound. So this is some distance r, and you want to find the intensity at this point. So how would you find that? So the intensity of the sound would be that the power over, because you consider that as a spherical sound waves, over 4 pi and then r squared. So that will be the area that intercepting the cell. So it's 4 pi r squared. So you can see the intensity of sound will be is proportional to inverse square. The farther away from the source, the weaker the sound intensity is. Okay, and based on this definition, the intensity, the unit for intensity is watts over meter square. Okay, so all right, so the other quantity that we are interested is the sound level. So what is sound level? Sound level is defined as beta, that's equal to 10 times dB, which is the unit for the sound level. We call that decibel, and then times log. This is not that natural log. This is based on the 10. So log, and then within the argument, that's sound intensity over the standard reference intensity. Okay, so this is how you specify the wave intensity in terms of the sound level. Okay, and so it's 10 times 10 times log of I over I naught. The standard reference intensity is 10 to the negative 12 watts per meter square. And so just to give you some idea, for conversation, the normal conversation, the sound level is about like 60 decibel. So you can actually put 60 on the left hand side of this equation, and then you can calculate what will be the intensity of the sound producing a sound level at 60 decibel. Okay, for rock concert, the sound level is about 110 decibel. Now, for pen threshold, it will be about like 120 decibel. Okay. Now, speaking of sound, the human hearing range is about like 20 hertz to 20 kilohertz. So that gives you the range of the human hearing range. Of course, each let's say animal will have a different hearing range. Okay, and that's kind of like common sense. And with that, I think we're done with the first part of chapter 17, and we're going to finish. There are there are three remaining concepts from chapter 17. One is the musical sound, and also the other one that is also related to musical sound, which we call that beats, and also the Doppler effect. We're going to discuss those concepts on Thursday. Okay.